Today is the last lecture of environmental engineering, and the topic for today is air quality and pollution. To kick off this topic, I wanted to read a quote by a famous person. It says, "But they're manufactured tremendous, if you're into this, tremendous fumes. Gases are spewing into the atmosphere. You know we have a world, right? So the world is tiny compared to the universe. So tremendous amount of fumes and everything. You talk about carbon footprint, fumes are spewing into the air, right? Spewing. Whether it's in China, Germany, it's going into the air. It's our air, their air, everything, right?" So I'm not going to tell you who said this. You can look it up. It's humorous, but a lot of it is true, and especially the last line, I think, really motivates some of why we're talking about this, right? It's going into the air, it's our air, their air, everything, right? So, unlike with water, where we have the ability to treat our water before we use it, and where the sources of pollution to water are discrete or at least can be traced. With air, it's very difficult to use air, to breathe it after it's been treated, or I should say, it's very difficult to treat air before we use it, right? And also, the sources of pollution in the air are not all discrete and cannot all be traced, right? They're disparate and spread out across the entire face of the earth. And that air can move wherever it wants to in the atmosphere. So it's a little bit of a different kind of system than with water. And because of that, we're not going to talk a lot about treatment technologies for air pollution. We're going to talk more about the problem of poor air quality, where it comes from, what's happening with it, why we're concerned about it. And unlike with water, a lot of the solutions for poor air quality come from things like policy and change in how we do life, how we practice our economy, things like that. Putting controls on pollution before it's put into the atmosphere rather than treating it or trying to sort of deal with it later after the fact. Okay, so let's see, what do I want to show first? I'll show this first. We're going to be talking a little bit in a minute about different effects of poor air quality. This particular website is talking about some of the trends in air pollution and also sort of why we might be concerned about it. And one of those is that air pollution is one of the leading risk factors for disease burden. So if you look at disease burden in the world, air pollution, outdoor and indoor, is in the top 5, right? So just behind obesity in terms of disease burden. You can go down and see some other things. You know, what are death rates from air pollution? So you can see some of these countries over here are most affected by that, and we'll talk in a minute about indoor air pollution versus outdoor air pollution and why some of this might be the case. How are death rates from air pollution changing? So you can see they are going down, which is really good. They've come down considerably over the last 30 years or so. You can see most of that is due to a decrease in indoor air pollution, whereas outdoor particulate matter and ozone have not changed that much over that period over the course of the whole world. So I'm going to look at outdoor air pollution for a minute. Indoor air pollution tends to be a big problem in developing countries due to the way that cooking and heating is done. A lot of solid fuels are burned, like wood or charcoal, inside the home. That creates smoke and fumes that can be very harmful to people. Outdoor air pollution is what we're going to mostly be talking about today. It's one of the leading causes in the world for premature death. You can see on this chart number of deaths by risk factor in 2017. Outdoor air pollution 3.41 is the estimated annual number of deaths in 2017 from air pollution, both outdoor and indoor, I should say. This talking about from ozone and particulate matter. Yes, we saw that graph already. Share of deaths from outdoor air pollution. So you can see in the Mediterranean, where population densities are high, where there's a lot of oil and gas burned, and there's a lot of kind of local atmospheric effects in there. You can see there's a large amount of deaths from poor outdoor air pollution. Also in Egypt, Cairo is one of the more polluted cities as far as air quality go in the world. Just a couple more quick graphs. Outdoor air pollution death rates by age. So highest among older people. It makes sense that the effects that we'll talk about in a minute get exacerbated when the immune system's compromised, as it is in older people. Let's see, I'm going to skim through some of this. One of the things I wanted to show is how emissions of air pollutants have decreased over time. So this is the United States, and we'll talk about some of these pollutants in a minute. But you can see that because of the Clean Air Act, which was passed 50 years ago, so in 1970 when this chart starts, air pollution in general has gone down significantly. And this is the case in most wealthy countries and developed countries that have passed laws and regulations that attempt to limit the amount of air pollution there is. We see decreases in a lot of these constituents. They're still high and above safe levels frequently, especially in cities. But it's a good news story, and this hasn't happened on its own. This has happened because we've made policy changes, we've made laws and regulations that have made this happen, and there's a direct relationship between the concentrations of these pollutants and the death rate. And we've seen the death rate attributable to air pollution decrease as these pollutants have decreased. Okay, so let's go to the lecture material. What are some of the effects of poor air quality? So we've talked a little bit already in class about global climate change. So I'm not going to go back through that again, but that's sort of the leading one you see, at least in the news these days. Thinning of the ozone layer, so we've talked about that as well. That's not as much of an issue now as it used to be when the use of chlorofluorocarbons, CFCs, was more common. We'll talk about ozone again in a little bit. Human health impacts are the big ones. So cancer, death, eye irritation, if you've ever been around when there's been like forest fires. There were some in the Columbia River Gorge a couple of years ago, and if you were outside for a long period of time, it really did affect your eyes. You started tearing up, and it was bothersome. Lung and breathing problems, and then increased cardiovascular disease, stroke, and heart attack. So it does increase your blood pressure to be breathing poor quality air. Impacts on building materials. So for civil engineering, this is really important. Corrosion of buildings or statues, and acid rain. Acid rain used to be a much bigger problem in the U.S. than it is now. We'll talk about it in a little bit when we get to sulfur-related pollutants, but because of coal burning, you had a lot of sulfur in the air, and that would contribute to acid rain, which would actually dissolve some of these building materials, things like limestone or marble, that were basic. When the acids hit it, they would neutralize them and dissolve them. So visibility is a big one. I wanted to bring up another site. So during this whole coronavirus pandemic, with a lot of people staying home and not going out and driving, we've noticed a significant drop in air pollution, especially in major cities around the world. this site is this is talking about a study on this that's been done, and it's kind of fun to look at. This is in Delhi, I believe, which is one of the most polluted cities for air quality in the world. You can see this cool little slider that you can move and see what I think this is a picture of Delhi last year around this. Oh no, this is November 2019, and then Delhi today during the sort of recent lockdown that's been put in place in Delhi. You can see this monument back here that's not even visible here. So visibility, a big deal. There's some other fun ones here. This is Wuhan in China. So July 1998, March 2020. Obviously, long time goes by between there. A few years difference, May 2017 to April 2020 in London. You can see kind of a difference. And of course, there's going to be other factors going on here, right? Than just there could be atmospheric issues. It could be a cloudy day. So let's see, aquatic and terrestrial ecosystems. So acid rain, heavy metals, ozone. Again, impacts on health, in this case of fish and wildlife. So air quality is regulated under the Clean Air Act, as I mentioned, 1970. The main purpose, or the main way that that's happened, is that the Clean Air Act established these national ambient air quality standards, which we'll look at on the next page. And these are regulatory limits for the levels of pollutants that can be in the air. And if places exceed those limits, then different processes are put into place to try to bring those levels down. So a lot of what we're going to talk about is what are the main pollutants. Table 11.8 in your book, it does a good job of talking about this, but these national ambient air quality standards relate primarily to 6 main pollutants, which they're right here. Particulate matter 10, particulate matter 2.5, carbon monoxide, nitrogen dioxide, sulfur dioxide, ozone, and lead. So technically 7, but PM is usually lumped together. Okay, so particulates, where do these come from? Mostly combustion of both wood, other fuels, diesel exhaust, from industry. It can also come from agriculture, from dust or smoke. And there's these 2 categories, PM10, which is all particles with a diameter less than or equal to 10 micrometers. And then PM2.5, which are even smaller, particles with a diameter less than 2.5 microns. The primary problem with particulates is health effects, particularly with PM2.5. So with PM10, when you breathe particulate matter that's 3 to 10 microns, that those particles you can breathe them in, but to some extent they're kept from entering the lungs by our physiology. PM2.5 can actually enter the lungs and get trapped inside of them, and that can be more problematic. They're also more problematic to treat for in pollution, like stacks and industry that's exhausting their exhaust. So particulates is a big one. It's probably the main driver of particulates and ozone together are the main driver of health effects. As we saw in the graphs we were looking at, we saw for outdoor air pollution, it was mostly tracking those 2 things. Ozone. So ozone, at least in the places where we can breathe it, this is generated in the atmosphere from a combination of carbon monoxide, hydrocarbons, which is like fuels, NOx, so nitrogen-containing compounds, mostly NO and NO2, and sunlight. When you combine sunlight, the NO compounds, and hydrocarbons, there's a complex photochemistry that occurs that creates ozone, which is O3. And we've talked about ozone before in a couple of cases. One was in the ozone layer. That's up in the stratosphere. That's good because it keeps UV light from getting down to Earth, so it protects our skin from UV. It also helps with the greenhouse effect. But the bad ozone is in the troposphere where we can breathe it. Ozone, O3, is really similar to O2. We breathe oxygen, we breathe ozone. But ozone is very reactive, and so when it enters the lungs, it can cause damage. And so the primary issue here is, again, health effects, although ozone can also be a problem for visibility. And actually, ozone itself can damage plants. If it's at high enough concentrations, it can cause damage to the surfaces of stems and leaves and so forth. Sulfur-containing compounds, the main source of this is fossil fuel combustion, and specifically coal. Some other industrial activity as well. And health effects are a big one here too, but a lot of coal power in this country and around the world has been cleaned up over the last 30 years or so, 20 years or so, due to, again, air quality regulation. And so the problems associated with sulfur compounds have greatly been reduced, including health effects, but also, as I mentioned, this is the main contributor to acid rain. But also visibility and deterioration of building materials. So with or without acid rain, the sulfur itself in the atmosphere can attack the building materials and cause corrosion of things like concrete and steel. Then we've got nitrogen compounds. So this is, again, primarily NO and NO2. Sources of this include fossil fuel combustion and particularly transportation. So cars don't put off a lot of sulfur compounds, but they do put off a lot of nitrogen compounds. And so transportation is the leading cause of these. It can cause health effects in and of itself, but a big problem with these nitrogen compounds are the conversion to ozone. Again, we saw up here as part of this chemistry. They can lower visibility themselves. This should be acid rain, not acid rain. And again, deterioration of building materials. So similar to sulfur compounds. And then we've got carbon monoxide. This is primarily an indoor-only type of problem in terms of the direct effects. This comes from incomplete combustion of fossil fuels. So when we run our cars, one of the exhaust products is carbon monoxide. And the effects are reduced oxygen circulation in the body. It prevents some of the binding of hemoglobin onto your red blood cells, and so oxygen can't circulate in the body as well. It's generally an indoor-only problem, although carbon monoxide, like nitrogen compounds, can contribute to the generation of ozone in outdoor air. And then the last national air quality standard is for lead, and again, that's mostly an indoor air quality issue, but doesn't tend to be a major problem, at least in our country. So these tables are from your book. The first one here is typical concentrations in clean and polluted environments of some common air pollutants. Over on the right-hand side, you can see the national air quality standards. Again, I showed this earlier. PM10, 150 micrograms per meter cube. PM 2.5 is lower. Carbon monoxide, nitrogen dioxide, sulfur dioxide, ozone, and lead. And instead of reporting concentrations of each of these on a daily basis for cities around the country, in order to kind of translate this into terms that are easier for people to understand what the air quality is doing, there's this thing called the Air Quality Index, which tries to look at basically what are the levels of air pollution on a given day relative to these national air quality standards, and then combining them all together. So whatever the level of a pollutant is relative to the national air quality standard, it gets some score. You do that for each of these 6 pollutants, you add them together, and you get your air quality index. And you can interpret that as, if you have a low air quality index, you're in good situation, air is considered satisfactory, air pollution poses little or no risk, all the way up to hazardous, where it's risky for everyone. in between, it can be unhealthy for sensitive groups, for older people or people with compromised immune systems, things like that. This is again from your book, and it just shows the number of days on which the air quality index values were greater than 100 during 2002 to 2012 in selected cities around the country. So you can see generally a decreasing pattern as air quality standards and regulations were put into place pretty much around the country. Here we are up in Oregon. We have very good air quality in Oregon compared to most of the country, and especially relative to other places on the West Coast, like in California, where you can see really high levels. In the Central Valley, in Los Angeles and the Central Valley of California are two of the most polluted places in our country. Some of this is because of population. A lot of it is also just due to geography. So valleys and coastal areas can be where you have terrain and coast, maybe mountains and coast, and air can come in, pick up pollutants from the populated areas, and then get trapped by the mountains or in valleys. That's where levels of pollutants can build up over time. So as you're emitting pollutants in some areas, that can just be spread out and diluted into the atmosphere. In other areas, it gets trapped and starts building up. And that's a lot of what happens in California, and why places like Fresno and Bakersfield and in the Central Valley tend to be pretty polluted. And then again, Los Angeles as well, because a lot of people, a lot of emissions, all kind of trapped by the San Gabriels and some of the mountains east of Los Angeles as well. So atmospheric effects play a very large role in air quality and air pollution and its effects. And your book goes into this a lot, and I'm not going to spend very much time on it, but the main thing I want you to understand is just how some very basic parameters in the atmosphere can have a large impact on air pollution. So what we typically see is this figure on the left. This is called unstable conditions. This is typically what occurs in most places, where the higher elevation you go, the lower the temperature is. And what that means is that there's warmer air near the ground than there is up above, and since warmer air is less dense, it wants to rise, right? And that means if we emit pollutants at ground level, that they will tend to be carried up and away from us because the warm air is rising. Conversely, sometimes we have atmospheric conditions like this figure, where this line right here is what we have, where with increasing elevation, we have increasing temperature. So the air is warmer up here than it is down here. We're emitting pollutants into this colder air down here. The cold air is less dense. It doesn't want to rise up above us. And so as we continually emit pollution, it tends to stay where we are. And that's called atmospheric inversion, and most of the worst pollution days in any kind of city are during inversion events. And this happens most commonly in valleys, coastal areas, things like that. This is another example of an inversion where you see what we expect for a while, right? This kind of a slope, and then you have this portion where with increasing elevation you have increasing temperature, and then it goes back the other way. So again, this can play a huge role in what will happen with pollution once it's emitted. And I just wanted you to kind of have a basic sense of that. Your book goes into great detail and really has a great chapter, chapter 11, on air quality and air pollution that we just don't have time to go through all. Finally, emissions control. So obviously source control and reduction is our best bet with air quality issues. We want to prevent the pollution in the first place. So not driving or or driving electric cars that don't emit pollution, things like that, it tend to be the best bets. But there are technologies to treat exhaust from different kinds of industries and sources. These technologies tend to be complex and costly. There's a couple great tables and figures in your book that go through a lot of these different kinds of technologies. They involve a lot of the kinds of things we've already talked about for water. So things like adsorption, filtration, biofiltration, oxidation, which is similar to like what disinfection can do. Electrostatic separation is a little different. We haven't really talked about that in terms of water treatment, but we can use electrostatics to separate out charged particles. Or if we can transfer the pollutants into the water phase, then we can treat the water just as we treat wastewater typically. So this is just one example figure from your book. It shows like, okay, we've got particulate matter. How do we determine what technology to use? Well, we can go through this flow chart and see, well, we can get these wet scrubbers or wet electrostatic separators, scrubbers or mechanical collectors, or we've got filtration systems or precipitators, again, wet scrubbers, so it's transferring the particles into the liquid phase where we could then bring it into a filtration unit or a clarifier or something like that. So I encourage you to look at the table and figure 11.19, 11.18 in your book that show a lot of these different kinds of technologies that exist. And again, we can't go through all these because they're very complicated and they address very specific air pollutants. In most cases, they're specific to the kind of industry that's putting out the pollution. But a lot of the same physical and chemical processes that we've already talked about for water. So that's just a very brief introduction to air quality and air pollution. I'm sorry I can't go into more detail and have more lectures explaining, a whole day on atmospheric conditions and how those work, a whole day on the different technologies there are. We just don't have time to cover everything, but hopefully that gives you just a brief intro to this really big topic.